Hello everybody, and welcome to this webinar organized by the Danish group of IABSE. And I should probably say good morning, good afternoon, and good evening to some of you, depending on your current time zone. We're actually close to 500 participants registered for this event from all over the world. And I think just while I slowly get us started, there'll probably be a few more logging into this webinar. I think it's very encouraging to see the great interest in this important topic, and we are fortunate to have this online format allowing us to get together and share knowledge, despite the very difficult situation that we have all gone through during the pandemic and that many countries are still experiencing. My name is Tina Vejrum, and I'm the chair of the Danish group of IABSE, and I have the honor of being the moderator of the webinar today. I have been a long-time member of IABSE for over 25 years actually, and I also serve as vice president of the association and a member of the editorial board of the journal. I'll introduce the journal shortly. In my daily work, I'm the vice president in COWI, that's a leading Danish consulting firm, and my area of responsibility is COWI's international bridge projects. And currently that includes the new world record suspension bridge, the 1915 Chirajara bridge, currently under construction in Turkey. Before we start, there are just a few practicalities. First of all, please be aware that this webinar is being recorded. And the reason is that we would like to share this knowledge with even more people than the ones who have the opportunity to participate live today. So it will be shared on IABSE's platform. I'll introduce today's presenters a little later, but just a short introduction before we get to today's main topic. To help us with the Zoom platform, we have two of the key persons working in IABSE's headquarters in Zurich. That's Mr. Firat Cicek and Ms. Bryndarika Bose. And if you have any questions of practical nature, how to operate this platform, or if you have questions to IABSE in general, please use the chat function. You can find it at the bottom of your screen. And then Brynda is ready to assist you, and she has prepared a lot of useful information that she will share during my introduction. For practical reasons, all participants are muted during the entire session, so please use the Q&A function to ask your questions, and then we'll address everything at the end of the presentation. You will also find that functionality at the bottom of the screen. So, to get us warmed up, and while the last participants join, I would like to give you a brief introduction to IABSE and to the activities in the association, and Brynda will be sharing useful links as we go along. IABSE deals with all aspects of structural engineering, and by that we mean the art of and science of planning, designing, constructing, operating, monitoring, inspecting, maintaining, rehabilitation and preservation, and even to demolition and dismantling of structures. And in doing so, we take into consideration technical, economic, environmental, aesthetic, and social aspects. And the aim of the association is to exchange knowledge and to advance the practice of structural engineering worldwide in the service of the profession and society. The association has over 2,500 members distributed in over 100 countries. There's quite a lot of history. The association was founded in 1929, so we celebrated our 90-year anniversary already. And the headquarters are in Zurich, as I already mentioned. There are a lot of activities, and I'll just make a small advertisement for the next webinar, which you can see on the side there. So already on the 10th of June, there'll be another webinar in this series. The publication is a good way for you as a member, or perhaps as a future member, to participate and publish your work. So there are these four types of publications: the journal Structural Engineering International with 4 annual issues, the green books, structural engineering documents on fairly focused topics, and this is a result of a lot of the technical work being done in the association. The blue books are focusing on case studies, and then we have the proceedings of the various congresses and symposia. At the center of the activities in IABSE, you'll find the national groups and the task groups. The national groups host a number of events like our webinar today. When it's possible to meet physically, there are seminars, workshops, there are site visits and similar. Also, the national groups, they really form the link between the various activities in the associations from the national level to the regional level and to the international level. So if you would like to have more information about IABSE, then I would encourage you to reach out to your local national group. The task groups are responsible for a significant part of the technical work within IABSE. At the top of sort of the technical work, we have the technical committee, which oversees the activities and makes sure that it has a required standard and quality. And in order to do so, the technical committee has 6 technical commissions, and they have the areas of responsibility that you can see listed on this slide. And then under these technical commissions, you'll find all the task groups. Currently, there are more than 40 different task groups within very specific topics. And if you visit the website, you'll find some very useful links to each of these task groups. You'll find an overview of their scope of work, the deliverables, and also the participants. So please do reach out if you wish to participate or just get more information. An essential part of IABSE's activities, that's the events. Normally it's physical events. The last year, of course, like everybody else, we've been forced to move more towards virtual events. But we very much hope that we can meet physically again in the next Congress, which will be in Ghent in September this year. Following the Ghent event, as you can see, there is the symposium in Prague in May 2022. And in September 2022, it's the Chinese group of IABSE welcoming us to Nanjing, and to an amazing opportunity, I think, to visit some of the world-class projects that are currently under construction in that area. And then last but definitely not least, IABSE offers a number of opportunities for young engineers. There is a dedicated program for young engineers, which includes reduced fees for students and young professionals under the age of 35. Special prizes at the conferences, such as the best paper presentation, and a number of social events during the conferences. And I would say sometimes some of us slightly older than 35, we are also invited to participate. And this is a great opportunity and good fun to participate and meet and exchange sort of views and experience. So now let's move to the topic of today's presentation, which is the tragic collapse of the Chirajara bridge in Colombia. And for those of you who have just logged in, this is exactly the right time to do so, and I'll take this opportunity to welcome you all again. I can see we're now over 250 participating in this webinar. So to set the scene, on January 15th in 2018, the west pylon of the Chirajara bridge, which is a cantilever cable stay structure, it collapsed during construction of the final sections of the bridge girder. And unfortunately, this collapse resulted in a number of fatalities. Shortly thereafter, the project insurer commissioned an independent investigation into the collapse of the bridge. And an international team of bridge experts was assembled to undertake this investigation. The investigations were completed in August the same year, and the causes of the failure and the sequence of the progressive failures of the individual structural components and thereby the entire mechanism of the bridge collapse was identified and analyzed. The key findings and recommendations from that investigation, as well as lessons learned from the unfortunate event, will be presented in the webinar today. And I would emphasize that today's presentation is technical, so what we will be dealing with are sort of the engineering and the technical stuff, which will be presented in this closed forum. And now I would like to introduce the 2 presenters. Presenting for us today, we have Professor Christos Georgakis, who is a professor of structural dynamics and monitoring at Aarhus University in Denmark. Before that, Christos held a similar position as a professor at the Technical University of Denmark. His research focuses on structural dynamics, aerodynamics, and vibration control, and with several patented technologies in the fields of wind turbine, vibration control, and bridge cables. He is also the co-author of the well-known book, Cable-Supported Bridges, Concept and Design, and he is an IABSE Fellow. In addition to his academic track record, Christos has a solid experience from practice, and he has played a key role in a number of landmark bridge projects. Klaus Ostenfeld has spent most of his impressive 55-year career in the field of major bridge design and construction internationally. Klaus is former bridge director and CEO of COVI, that's a leading Danish consultant and actually the same company where I work today. Klaus served as the president of IABSE from 1997 to 2001, and he was also chair of the IABSE Foundation. Today, Klaus is an honorary member and a fellow of IABSE, as well as of a number of other professional organizations. Klaus has taken a particular interest in education, in structural understanding and behavior, and today Klaus Ostenfeld is an honorary professor at Aarhus University and working closely together with Christos. And in addition to this, Klaus is also an independent expert consultant. So before I just finally hand over the stage to Christos and Klaus, a few practical details. So please again be reminded that this webinar is recorded, and please use the Q&A function to ask your questions to the presenters. We'll have the Q&A session at the end of the presentation, but you can post your questions at any time during the presentation. And finally, any questions of practical nature, please use the chat function. So with that introduction, I'm very pleased and honored to hand over to you, Klaus and Christos, and I'll stop sharing my screen.
Okay, thank you, Tina. Can you all see us? Are we on the main screen now? Very good. So thank you very much, Tina, for that very kind, generous introduction. And good day to everyone. I understand it's all different times of day for various participants here. Thank you to IABSE for organizing this, and thank you all the participants for joining this webinar. So Klaus, would you like to say something before we continue?
Well, of course, I would also like to say thank you for this opportunity to present a case which is a case that I think the bridge engineering profession and all structural engineering profession could learn from, because this is, of course, was a very tragic collapse of a major bridge structure, and that is certainly not a thing that we would like to see happen. Unfortunately, it does happen once in a while, and also it seems to be things that cannot be apparently avoided, but we can at least do our best as professional engineers to convey the findings of the investigation and make everybody aware of the risks that we are facing in our everyday life. It's very important structures that we are dealing with, and we have to take it very seriously. And I also want to emphasize, as Tina did in the introduction, that we are talking amongst technical people. We will not be entering into any discussion about the potential legal issues as an outcome of this unfortunate event. So we're talking technical people to technical people. And that's all I want to say. But thank you, IABSE, the organizers, for making this possible, this webinar, and I'm very enthusiastic about it. So let's move on.
Okay, I think we need to share our screen. Is that what we do? So all right, Tina, can you nod if you can see the screen? Yeah, very good. All right, so as we've said several times now, this is a presentation of the investigation that we undertook on the collapse of the Chirajara Bridge. I want to go straight into a video of the collapse. That's how I'll just turn the screen a little bit towards me so I don't fade out. And then when Klaus's turn comes, he'll turn the screen towards himself. So I'll just I'm going to put this video on, and it's just a 17-second video. Just pay attention to the left top corner where you see the bridge. The video itself was taken from a camera on the road. It's a security camera on the road, and it was not intended to be monitoring the bridge. It was monitoring the road, but we just happened to be lucky in this instance that this road security camera was also looking at this portion of the bridge at that time. Okay, so I'll play this video of the collapse once, and then we'll do it one more time. All right, so there it is. It's just a matter of a few seconds for the whole thing to collapse. So we do it one more time. All right, and that's it. That's a 17-second clip. That's all it was. In fact, the total collapse was took much less time overall. Okay, so now I want to describe a little bit some of the generalities related to the project before Klaus gets into some of the more specifics relating to the design of the bridge and some of the deficiencies that we found along the way. So this is the site. This is what it looked like after the collapse. You can see the bridge. It's a cable-stayed bridge. It was under construction. Main span is approximately 285 meters, and a 3-span cable-stayed bridge with reinforced concrete pylons and a composite girder. The cable stays are parallel monostrand stays, and it was the pylon, as you can see to the right, in the direction of Bogota, which collapsed. So I'll tell you more about the actual location of the bridge and which road it was intended to improve in the coming slides. So the bridge was insured by QBE, an Australian insurance conglomerate, and QBE contacted ONC loss adjusters in Bogota, who then contacted me and asked if I could lead the investigation on their behalf to try to determine the causes of this collapse. There was already another investigation being undertaken by the other parties that were involved in this, but ONC had decided that we would be the right people to try to investigate this. So I agreed to this investigation, and then quite quickly afterwards I assembled a team of international experts. That was one of the conditions of doing this, that we had a grouping of international experts, and that this investigation, so that this investigation could definitely be considered independent. From left to right, Siegfried Hopp was part of the main team from Leonhard Under and partner, Yoso Fujino from Yokohama National University, Klaus Ostenfeld, who's sitting next to me, from Aarhus University, and KHO Consult. And then we have Eilef Svensson, who was from ES Consult. So the 5 of us composed the main team of experts. but we had enormous amounts of help and from other engineers that were involved, and without which we could not have completed this this investigation. So we have Lasse Hindhede from Ramboll. He's actually currently at Ramboll. At the time he was employed with me. Martin Kokstrup, also the same, employed within my consultancy, and now he's at Ramboll. Michael Muller from Leonhard, Andra and partner. Francesco Sibira, also from Leonhard, Andra and partner. They mainly undertook the independent Category 3 investigation of the bridge. Gregor Fischer from Technical University of Denmark, who did the material testing, and then there was Thomas Rompel, who from Smolczyk and partner, who was involved in the geotechnical investigations. Okay, the bridge itself collapsed on January 15th, and approximately 2 months later, we took a flight from Copenhagen to Bogota on March 18th. There was a team of 4. There was Lasse Hindhede and Martin Kokstrup, Eilif Svensson, and myself. We flew down to undertake the necessary investigations down there, which involved interviews with people, collecting material samples, going on site, photographic, of course, evidence, and any kind of other material documentation that that we could collect. So where is the bridge? The bridge is located where at the position where you see the yellow star on your screen. So the idea is that this highway, which connects Villavicencio and Bogota, it should be, the intention was to improve the highway so that the time it took to go from Villavicencio to Bogota or the other way around was reduced. And at this specific location, you can see this sort of horseshoe bend in the road, and that's where the bridge crosses. So you can understand in this, and you saw it from the pictures also, in this deep valley, this particular bridge would cut a lot of time at this location. Okay, but another thing I just want you to note, and I think you noticed that from the pictures, the terrain is very mountainous here in this region. There's nothing flat or easy about this. It's a very, very difficult and a jungly type of terrain. Okay, I'm not going to say too much about this because Klaus is going to talk a little more about the specifics of the bridge here. But again, I just wanted to point out that the main span was about 285, actually 286 meters. The side spans around 69 meters. And pylons were monopiles at the base. So we had monopiles going into the foundations, and I think the rest I've already said, so Klaus will tell you more about that in the coming slides. Okay, I wanted to just show you what the bridge looked like during construction. So this is a screenshot from a drone. You can see this diamond-shaped pylon. You'll see it better in the next slide. Just look at the side, you can see sort of the width of this pylon. Also some of the post-tensioning, some of the ends of the tendons can be seen just at the knee location of the pylon. Also the construction of the girder with the steel beams and the concrete surface. Additionally, you can see, well, if you really pay close attention, you can see some of the details of the cables. Okay, in the next slide, you can better see the shape of the pylon itself, this diamond shape. And what I wanted to point out here is this concrete diaphragm, which exists between the legs of the pylon on the lower half of the pylon below the girder. Okay. Finally, I have this video here. Yes, it started. Might be a little bit slow. Okay. If it's too slow, we'll pass it up. But the idea was to show you, to give you an overview of the bridge, and then to show you how the bridge actually went from the Villa Vicencio side across the valley into a tunnel. I think you can see the tunnel in the distance, so we don't really need to see the video. But you can kind of make out, if you pay attention behind the cables, you can see the wreckage of the other half of the bridge, which collapsed. Okay, and then this is just a picture of Lasse, one of the engineers who was instrumental in the investigation. I just put it in there just to show you the sort of conditions that we had there. We had to get this abseiling classes, or some sort of a crash course, so that we could go down the mountain and climb all over these very large pieces of bridge, which formed the wreckage of the collapsed pylon. Okay, finally, in August, on August 31st, 2018, after a little over 6 months of investigation, we submitted the report on the investigation of the bridge collapse. And I think as far as we're concerned, it's definitely a very comprehensive report, which I think details pretty much everything that we observed and found during the investigation. Okay, so this is sort of an introduction and some of the generalities surrounding the investigation, and now I'm just going to pass it over to Klaus so he can start to get into some of the more nitty-gritty details of the design itself and the deficiencies. All right.
Thank you, Christos. Yeah, this was a joint effort, as you can understand, and that's why we have decided to share the presentation here. What I will do here is to try to give you enough detail about the structure and its various constituents in order to understand, after my part of the presentation, the collapse mechanism that Christos will then talk about. So basically, on the face of it, what you see is a rather conventional cable-stayed bridge. A single-span conventional cable-stayed bridge with a 286-meter main span, nothing in particular. Actually, it should be a very simple thing to design a bridge like this and construct it. But it wasn't, apparently. So the structure consists of the main pylons in concrete. This is actually just a shot of the final element model, which was used for the analysis of the bridge in detail. But it shows in an isometric view here the system with the cables attached at the edges, providing the torsional rigidity for the deck. The deck itself, as you will see later, is not torsionally stiff. It is actually very slender, torsionally wise. So all torsional rigidity basically stems from the fact that we have two sets of cable stays attached to either side of the deck. When we look into the pylon itself, again, it looks fairly conventional, diamond-shaped, basically, assembling all stays in the top of the pylon head. there, and actually, of course, straying both sides from the top of the pylon here. And then we should pay a special attention to the fact that we have rather, maybe unconventionally, a rather slender link slab connecting the two knees, as we call them, of the pylon legs, which of course would need to be held together to resist the thrust by and take the deviating forces, axial forces in the legs, and make sure that we deviate the forces towards the common foundation. Maybe also a bit unconventionally is the fact that we have a diaphragm, a fairly thin diaphragm, 0.5 meter thick diaphragm between the 6 meter deep legs of the pylon. As you can see in the cross section here, rather thin, slender members connecting the two legs. And as we shall see later, this diaphragm actually played a major role in ensuring that the bridge was standing up until the very moment when it collapsed. In fact, to disclose that already now, the linkage provided by the link slab was far from sufficient to redirect the forces in the legs towards the foundation alone. So as we shall see, as it often says, the devil lies in the detail. And that was unfortunately also the case for this particular bridge. A basically conventional bridge had a lot of deficiencies in its design and construction. Let's focus on the tension link slab. It's again a rather thin slab, about 6 meters wide, same width as the depth of the pylon legs, and I think 0.5 meter thick. And then pay attention to the fact it was post-tensioned by 14 cables, actually cables, they were only strands, transversely, should be these ones, 12 cables, one strand each, were linking the two knees of the pylon. So that is, of course, a very, very minimal post-tensioning. And further, one should notice that the ordinary reinforcement in this, the mild reinforcement, unstressed reinforcement in this deck slab was not projecting into the leg. So in other words, there was no continuity at this particular interface between the link slab and the knee of the pylon. No other connection than these strands, the 12 strands that I mentioned before. So that's really an eye catcher. Then in addition, this slab was post-tensioned in the longitudinal direction of the bridge transversely to the link slab by actually a higher amount of bridge dressing for some reason, which is not particularly clear. So if you look at it closer, you see the transverse strands and the longitudinal cables, each consisting of 8 strands in the longitudinal direction of the bridge. And at this particular point, no connection with ordinary reinforcement. That will be demonstrated also later. And of course, that was an important observation when you just look at the design as such. Another observation, the pylon head, again, rather traditionally, as it is commonly the practice in many places, you improve the top structural strength of the top of the pylon by encasing a steel box in which you can actually efficiently anchor. It's not shown here, but the anchor itself, but you can anchor the individual cable stays, which will, you have to imagine they protrude like this from the top of the pylon head in all 4 directions towards the deck. So in other words, the top is of course subjected to a horizontal pulling apart force, to put it primitively, equal to the accumulated horizontal components of all strands, of all cable stays. Now we found again that it was quite obvious that the steel casing would not be sufficient to resist these forces, neither, and the reinforcement in the concrete encasing the steel box was not sufficient either. So even the combination of the two would not fulfill ordinary design criteria for these forces. And this apparent crack here, of course, you will see later on in some of the photos from the drone inspection of the still standing pylon. Further, the shear connectors, who were supposed to form a composite action between the steel box and the concrete, were not adequate either. Once you start verifying it, so the pylon head, as such, was not adequate design-wise. The deck is again a fairly conventional deck. Let me go to the next one, it's maybe easier. Consisting of a plate girder outside, inclined more or less in the same direction as the stays would hit it, with a flange on the bottom, and then cross girders once in a while transversely, with a concrete deck cast on top. And actually at the time of the accident, there was still missing the last few deck castings on that particular cantilever when the collapse occurred. So the idea is you erect the steel works first, and then you cast this concrete deck on top with shear connectors. The shear connectors were changed from original studs to channel pieces welded on top of the cross girders. A very simple composite bridge deck, but actually, as I mentioned earlier, without any torsional rigidity at all torsional fixity provided by cables at both sides. The detail of the connection, the anchorage is located along this line, and here you see that with the E, we noted the eccentricity imposed on the deck, which it was not designed properly for, and instead of following, which logically would have been the case, arranging the detail in such a way that the anchor, the cable stay force would go directly in the same plane and same direction as the web. So this eccentricity was cause for quite some bit analysis-wise overload of the steel in this region. The cross girder you see here, a 9.5 millimeter plate going transversely, of course, connecting the two outer plate girders. Now, I mentioned that the girder is not torsionally stiff, which was, of course, the case for the well-known Tacoma Bridge failure in 1940. That was a suspension bridge. I'm not going to play this video because I think it has been shown so many times that you are bored, but this all illustrates what happens. We should all remember that when we do our designs. The designer had made a provision for including some kind of a wind fairing onto the deck, but it was not installed at the time of the accident, and whether it was actually planned is not known. But at least there was a design in the documents that we found. Whether it would have helped, I doubt it, because the real problem is the release of vortices at the bottom of the girder, which makes this girder non-aerodynamic in any case, and also would therefore not prevent any tendency to get into some kind of undesirable vibrations during certain wind speeds. Then I would like to focus a little bit on the abutment layout, which was rather special, I must say very special in many cases, but founded on concrete caissons. And this particular part I'm pointing at here, I hope you can see it with my red laser, is a girder, a beam in which the 4 backstays on each side are attached. Pay attention to that one, because it was attached then to a transverse beam and then again to the girder. I'm going to more detail about this now. Here you see this transverse beam, the girder on the right side, and these beams on the top, on the bottom, onto which the backstays were anchored. In between this assembly, which is all holding together and sticking into a concrete box, which is fixed, temperature movements would make the girder move back and forth in this direction at the same time as horizontal components from all stays is transmitted through this assembly with eccentricity, you will notice. Further, there were at this point here, this is a design, a sketch indicating the analysis model with springs and so what, but actually there is a rubber piece interjected here, a neoprene bearing type, which will cause in itself the girder to move when the temperature movements at the end, when the girder expands and contracts, it will not move horizontally, it will actually move inclined in a plane perpendicular to this rubber bearing, which means, of course, that the expansion joint would never align, well, only align in one particular position, but it would not align always vertically. Whether that had not been solved at the time of the investigation, I don't know how it would have been solved actually, because the movement will be forced to be along this inclined line. And here you see a cross-section of this particular area of the abutment caisson. There are the beams, the rubber bearings, the caisson post-tensioned vertically, I would say in a normal conventional way, and then the caisson foundations or piles below. So the cable tension would be subjected here at this particular point with the through the neoprene bearings. Horizontally, horizontal section, these beams were connected to the transition beam through vertical web beams here, meaning that any tendency for horizontal component would have to go through a beam which is designed more as a beam taking vertical normal moments around a horizontal axis rather than a vertical axis. So it was actually overloaded. It would form more or less a plastic hinge formation here. So it was a very, very peculiar type of abutment. So here you see an illustration of what would happen with the slightly inclined cable plane acting to a beam with bearings which were inclined in the other direction, but horizontal in the transverse direction. So actually they would be subjected to a horizontal shear force, not accounted for. And then the beam itself was not reinforced adequately to take the spreading of this stay force out to the two supporting beams. So to sum up, there are lots of details in this, of course, but to sum up in a reasonable short time, we could say that the stay force transfer in the pylon head was inadequate. The box, the concrete encased box, the stay anchorages and the bridge girder web with eccentricity causing overload to the steel and the girder. The horizontal tie between the pylon knees I would say not less than catastrophically insufficient, with inadequate amount of post-tension cables and no continuity of reinforcement. The abutment design and bearing structurally inadequate in many ways, and a very, very complicated setup. And then the aerodynamic stability was also questionable. And what I didn't mention, by the way, is that the whole thing led to, as we shall see later on in Christos, when he explains how the bridge actually failed, it failed in a very fragile way, completely unexpected within 2.5 seconds or something like that. So no way for anybody to escape. The diaphragm played a very important role in ensuring that it did not happen before, because the horizontal reinforcement in the diaphragm wall was in fact protruding into the pylon legs, and that delayed the fatal accident. Then it was also, but I'm not going into a lot of details, but the foundation caisson was an 8-meter diameter caisson, also had some deficiencies. So there was quite a bit of discoveries to a design which actually on the face of it looked quite normal. The devil lies in the detail. This is more or less repeating, but yeah, I don't think I need to go further into that one. So I think over to you, Christos, to explain what then really happened and why it happened and how it happened.
Okay, thank you very much, Klaus, for going into detail with all those specific deficiencies. And I think that you can see from, or I hope you've understood from the presentation that Klaus just made, that there were a lot of deficiencies, but for the collapse itself, of course, there was one major, or let's say main deficiency at that point of the construction, which led to the collapse. So let's go a little further into what this is. So I'm just presenting this particular slide again, because now I want to just focus a little more on the finite element modeling. So this is the model that was used. It was a full 3D nonlinear, not just geometrically, but also material nonlinear finite element model, which we ran not just statically, but also dynamically. And this is very important because, as I will point out in one of the subsequent slides, the dynamic component of this was very, very important ultimately. We used all of the different types of material models and different types of elements which should be used for the different parts of the bridge, as one would do in the design or analysis of such a bridge. Okay, so one of the important things was the material model of the concrete itself, and this turned out to be a little more involving than we thought at the beginning. And that's partly because we had to try to understand exactly what sort of behavior we had in the concrete, in the diaphragm. That's the element, that's the wall between the legs. And through a little research, we found that in fact the diaphragm would not be able to behave in a ductile manner, but it would start to crack and fail in a non-ductile manner just because of the level of reinforcement. It was an under-reinforced, if you want to call it that, characterize it as an under-reinforced diaphragm. So a properly reinforced or over-reinforced diaphragm might have behaved in a more ductile manner, but these under-reinforced diaphragms or elements will tend to behave in a non-ductile manner. So this particular picture gives you, or this figure gives you an idea of what might have been happening at the interface between the pylon leg and the wall when we introduced the deviation forces coming from the top of the pylon. So now the leg wants to spread apart and as it's pushing, there aren't enough tendons in the link slab to hold these deviation forces. So as the legs are pushing the lower legs apart, the wall is there trying to retain these legs, and the reinforcement is effectively the only thing holding these legs together. This is me on top of the link slab and the wall, the collapsed link slab and wall. And if you just look at the side of the wall, you can actually see the reinforcement, just very, very small bars, which are relatively sparsely spaced for that size of wall and for this size of construction. Yeah, you can just see these reinforcing bars down here, these little bars. That's effectively what was holding the two lower legs together.
The tendons.
And then we have the tendons here. You can see that Klaus highlighted earlier. We have 12 of those, 12 single tendons. And through our calculations, they could only provide about 25% of the needed restraining force for the deviation forces which existed on the bridge. Now, if you look more closely at these are photographs that we took on site of the reinforcement, which was coming out of the wall and connecting the lower legs. And here it's quite obvious to see the yielding and necking of the reinforcement. So there definitely was pulling action, which led to yielding of this reinforcement. This reinforcement was not sheared. It was not mangled in some other way. It was definitely pulled apart and yielded in these locations. And the same happened eventually to the 12 tendons. So once there was enough elongation of the system, once the legs had split apart enough, then we ended up getting rupture of the 0.6 inch strands. And you can see this necking occurring there. So now the important thing in the finite element analysis is the introduction of the dynamic component, because we did a static analysis of the bridge in its current configuration, in the configuration just before collapse. And in fact, we found that the bridge was able to stand. It was not collapsing under the loads that we had placed on it. But once we introduced a dynamic analysis, or undertook a dynamic analysis, we found that in fact there was a dynamic amplification factor of the loads of approximately 2.0. That means that once the reinforcement started to yield and rupture, the reinforcement in the diaphragm wall connecting the two lower legs, once the deviation forces were enough that this reinforcement started to rupture, then we got a dynamic amplification of the upper loads of about 2.0, and that was enough to lead to the full collapse of the bridge. In fact, when we just tried to model the bridge without any other information other than the loads that we knew were on the bridge at the time, the materials that were used, and the different elements, the way they were positioned, we got to 99% of the actual load on the day before the collapse happened. So we were very, very close in our analysis to the actual loading scenario that we had on the day. So we're very, very confident from that analysis that pretty much gave us the full picture of what was going on and what happened during the collapse. So just to kind of show you what we got from the finite element analysis, here we can see at time 0 We have cracking beginning to occur in the upper corner of the diaphragm because of these deviation forces that we talked about. 0.2 seconds later, we have the elongation of the crack and the opening between the leg and the diaphragm. And then subsequently, about half a second later, we have full crack formation from top to bottom. And we have the leg completely coming off of the wall or delaminating from the wall. So that's, in a nutshell, the main mechanism which led to the overall collapse of the bridge. Now we have a video. It's about a 2-minute video. There's no sound to it, but I'll put that on. And what it does is it shows what the bridge pylon with the girder looked like before the collapse, and how what sort of forces were involved and what sort of mechanism was involved in the overall collapse of the bridge. So let's see if we can get this going. All right, so we see the forces here. Now we've taken away the girder, and we just have the pylon, and we have the forces from the top going down through the legs, and these obviously cause some deviation forces. These are these green arrows that we see. Now these deviation forces are pulling the bridge pylon legs outward, but we have no extension of the link slab reinforcement into the legs themselves. Then we have some longitudinal post-tensioning. Now, Klaus said we're not sure what it was used for, but we think it was used for an initial design, which was for the cantilevering method, which was not employed in the end. And then there are the 12 single strands, which go from one pylon leg to the other through the link slab. Now, these 12 single strands were meant to carry all of this deviation force, but as I said to you earlier, it just was not enough. So what happened is that as the forces were too great for the tendons and the reinforcement we had at that location, we ended up having a crack initiating. So we have a crack initiating in the corner of the diaphragm. The crack eventually, due to the increase of forces as we're constructing the bridge, opens up further. And then at some point, we begin to have yielding of the reinforcement. And then very quickly afterwards, due to this non-ductile nature of the material, we have rupturing of the reinforcement. And this all happens very fast. So we have a kind of unzipping of the reinforcement between the wall and the leg occurring. You can see this is all happening within less than 3 seconds. So within a time frame of less than 3 seconds, we have full delamination of the legs and the diaphragm, and then the subsequent collapse of the bridge. So the sudden nature of the collapse of the bridge without warning can be attributed to the brittle design of the diaphragm. So one of the key observations we have, or at least it's one of my key observations, that ductility is a form of redundancy in a way, because if the diaphragm leg combination was reinforced in such a way that we had a ductile behavior, then there would have been some warning. The workers would have seen the cracks initiating, and they would have been able to stop the construction, get off the bridge, and initiate some investigations. There was no possibility here for that. Once the reinforcement yielded, it almost immediately ruptured, and then the whole series of reinforcing bars from top to bottom just unzipped, and the leg moved away from the diaphragm. So that's pretty much the collapse mechanism in a nutshell. And I think after this we have Klaus with some project organization comments and recommendations.
Thank you, Christos, for this explanation. Now we just to have a brief look to finish off, to try to identify what happened and why did it actually happen, to the extent that we were able to sort of identify at least some findings that we could use to take with us in the future. I want to point out here the organization. We have the owner who has made a contract for operation and maintenance made a contract for construction with a main contractor, rather conventional. Initially, it was contracted to one party. We have no names on here, but that's how it was started out, and a phase 2 design, so-called phase 2 design, was developed as a basis for construction. For reasons that I at least don't know, maybe Christos does, this contract was cancelled. And the contractor was dismissed at that time, and another contractor group was engaged to produce a phase 3 design, presumably based on the existing phase 2 design. And then, of course, it was subcontracted to suppliers and others, and a designer who could actually do this phase 3 design. That's the rough indication of how it was organized. Nothing special really, except for the cancellation, which proved to be crucial. The contract, which was a design-build contract, have these key elements. The new contractor assumed all works and risks with apparently insufficient review. That's something to underline. He was also supposed to accept the phase 2 design as a reference design. And he was supposed to perform a phase 3 design for construction. And the time schedule was rather concentrated for this. It might not have been completely impossible if they had decided to continue the phase 2 design, but actually the phase 3 design was a different one. In particular with regard to the areas that we now have seen caused the failure. Also, the new design contract stipulated the procedures for the design and the time schedule for the construction, all also quite standard. And they had nominated which key personnel that was a precondition for the contract should be involved. And then, of course, they should implement a quality management system. Now, just to show what one of the major differences between the previous phase 2 design and the new phase 3 design that you have seen on all the previous slides. This is actually the tie beam design for the phase 2 design, which supposedly should have been the one they would be continuing in the phase 3. And this time, at that time, without the diaphragm below the crossbeam. So a very conventional diamond-typed pylon with a substantial cross tie between the two legs where it was needed. But apparently that one was dismissed and replaced by the one we have seen in the previous presentation. So what do we observe when we try to dive into the documentation for this entire project, which was a major study, but actually we couldn't find much of an evidence of which selection process had been used. We couldn't identify any reason why the phase 2 design was abandoned and replaced by the phase 3 design, which was quite different. And remember, the time frame was very short for designing it. So actually it became a new bridge to be designed within, we can say now, impossible short time frame. And this new concept implied, as you have seen from the previous presentation, the pylon design was changed with a new design. Here it is indicated that the tire capacity was reduced by a factor of approximately 13. I don't know if this number still stands, but that was at least what I found in our documentation. And the stay anchorage system, the pylon top was different. The anchorage types at the bridge deck, you remember maybe from the previous slides that I talked about eccentricity implied between the cable plane and the web extension. In the phase 2 design, they were aligned. So it was a more conventional attachment of the cable stays to the webs in perfect alignment without eccentricity. And then, of course, the abutment and bearing layout, which is a bit peculiar in this on the phase 3 design. We couldn't find any method statements for construction. The interface management, which I normally also emphasize, is extremely important when you have many parties involved. Who does what, and how are the interfaces managed throughout the process? Not formalized here. So, are you doing this, or am I doing this, or is it being lost between two chairs, or is it being duplicated? All this rather simple stuff, trivial stuff that needs to be taken care of, but apparently not. The time schedule was unrealistic. Then further, there was no records of independent checking of the phase 3 design, which hopefully would have caught the major deficiency. And then in certain instances, the level of documentation was down to the, I almost would say ridiculous level of using WhatsApp only as a serious documentation that is not approvable. So these were all the observations which accumulated, of course, have contributed to the tragic outcome of this bridge construction. So once we then start assembling all these findings, you could say, well, we have to, the conclusions are almost quite obvious, that a independent category 3 check must be done for a major structure. This structure was not adequate for its purpose, and it had always an imminent risk of failing in all phases. As Christos was mentioning, it came up to the very point of safety factor 1.0 with 99% of it. And then when they were ready to pour the last piece or next last piece of concrete on the deck, it collapsed. That had not been cast on the second half of the bridge. That's why it was still standing when the visiting team passed the construction site. But it was probably standing with a safety factor of 1.01 or something like that. Then the undocumented changes during construction, of course, is not acceptable because it is very important always to know whether the construction follows the design intent laid down by the designer. That has been the cause of many failures in the past, in particular for scaffolding structures and so on. And why did it occur, and why did it pass unnoticed? That, of course, is very difficult to completely know. But one can conclude at least that it was a series of errors and omissions that altogether came beyond what the structure actually was capable of being subjected to and hold up for. So I'm not going to point out any area in particular, but just conclude that the whole setup seemed to be ill-fated throughout the process, since the phase 2 design was abandoned and the new contract was entered into. We looked upon the existing structure, and that was part of our mandate to see whether they should just rebuild the collapsed part and reuse the other half of the bridge. But actually we came to the conclusion that it was so full of all these errors that we saw from the previous discussion that it would not be salvageable. So it was decided to do this. So that was the dramatic conclusion for that bridge. That this time without any people, without any casualties, because it was planned. But it actually illustrates again the failure mechanism that Christos was just explaining a little while ago, with the zipper effect, the very rapid evolving zipper effect between the diaphragm and the leg. And actually the insufficient tendons were acting like rubber bands for quite some time because they were ungrouted, so they could be elongated quite a bit before they finally broke, but they were far from sufficient to prevent the catastrophic failure. Further on, the horizontal pressure increases as the failure mechanism evolves because the angle between the legs, top and bottom, increases. So these are the lessons. I don't think I will read them up, but I think if we use what is normally the good practice, and we're very fortunate for that, good international accepted practices all the way through, and if we are very much aware of the fact that we should at all time know what we're doing and don't do it too fast, so we know exactly what it's doing. And structurally, I'm personally advocating the idea of what I call intelligent check of all structures. Detailed check you can always do by computer, but sitting down and doing a few calculations on the backside of an envelope very often would reveal fatal mistakes and catch them and simply ask the question, let's look at this again. So that would be my concluding remarks, and maybe this little word here, that we can generate the right quality with use of the qualified people. Checking will not do the job as such, but it's the one that we will use for picking up mistakes if they nevertheless are being made by even qualified people. So with this, I will say thank you on behalf of myself, and I guess we are ready for questions that you might have. Thank you.
Thank you very much.
Thank you very much, Christos and Klaus, for a brilliant presentation and for sharing these technical learnings so openly. There's a lot of food for thought in your presentation. Let's open up.
I want to interrupt and just say thank you to Thomas Kabel Peterson, who's our postdoc here at Aarhus, who helped us very much with this presentation. We almost forgot to thank him. Sorry.
He's right next to us. So.
Thank you, Thomas. Much appreciated. I'll just open the floor to questions, and I can see we already have 28 questions, and there are probably more coming in. Just sort of service message for everybody. I will only be focusing on the Q&A part of the conversation. So whatever is taking place in the chat channel, I will not deal with it during this Q&A session. So if you have something placed there, then please copy it to the Q&A. the way we're going to do this, I think I'll read these questions out to Klaus and to Christos, and there may be some of them you have already answered sort of during the second half of the presentation. So we'll try and deal with this on the fly, and there may be a bit of repetition. So I'll do my best to manage the process. The first question we got in from Alessandro Ponzone is a category 3 check. I mean, an independent check of the project before the construction had been made. If yes, does exist evidence of the results of this process?
I think I can answer that one, because maybe that question came in before my second half. In the second half, I did underline the fact that we could not find any evidence of category 3 check or any other kind of independent checking of the design. So the answer is it was not done, as far as we are concerned.
Thank you for that. That was a clear answer. Here, I think it's more a comment from Marwan Farouk. The analysis shows a symphony of errors. I think you would agree.
Correct.
Let me just, here's another one to third party.
It's more or less the same question as the first one.
Yes.
Yeah.
Thanks for a nice presentation. How do you say that the diaphragm reinforcement delayed the collapse?
Yeah. I don't think the diaphragm reinforcement, I mean, other than providing some minimal restraining force to the legs, diaphragm reinforcement didn't really delay the collapse. If the diaphragm reinforcement was sufficient so that we had a ductile behavior, then we could have seen the cracks occurring early on so that some action could have been taken before the collapse. But the way it was reinforced, it was very sudden. The collapse happened suddenly in a very non-ductile manner. So I'm not sure if I'm answering the question that you have, but sure.
Well, let me try to supplement. I tried to interject a comment after Christos before. I think you explained very well, Christos, the zipper effect. So what delayed the real initiation of the collapse before it actually started as a collapse, I think we can say was a progressive yielding of the rebars, starting with the top ones, where the elongation was the longest, and then progressively, like a zipper, going all the way down as a collapse progressed, as you saw on the video. But I was saying also that the strands, the 12.6-inch strands going all the way across, they were unbonded, which means that they could actually take quite a bit of elongation before they ruptured, but they were far from sufficient to stop the collapse. But they acted a bit like, you might say, rubber bands before they, maybe after 1/2 meter separation or something like this, finally ruptured. So I see the failure starting with the crack in the concrete between the link slab and the diaphragm and the leg. Once that crack forms, no tensile forces can pass through the concrete anymore. Everything passes through the strands and the rebars, and the rebars then subsequently rupture one after the other in a zipper effect very quickly going down, while the legs separate and the rubber band extends to about 1/2 meter, and then they rupture, and then no more restraining forces exist. I think that's basically what happened. Mm-hmm. Would you agree?
I agree with it.
Yeah.
Thank you. I think there's a related question here. I'm just jumping a bit through the list to try to group it a bit. The question is related to the diaphragm. Was this a precast element or was it a cast in place element?
The diaphragm was a cast in situ, so it was not a precast. So it was cast progressively. It started from the bottom, and the walls and the legs were cast together in stages.
Maybe the idea was to create sort of a huge vertical beam with the pylon legs acting as flanges and the diaphragm as a web, if you see what I'm talking about. A cantilevered vertical beam with a variable depth being the transverse direction.
Thank you. There are some questions here, I think more related to perhaps the bridge doing service. Here comes a question. Given the transverse section of the bridge, so the bridge deck, with a low torsional stiffness, would you consider that despite main deficiencies that caused the collapse, that the aerodynamic forces would have caused a big problem during service? That's probably one to you, Claus, related to the Tacoma comparison.
Well, Christos is an aerodynamic expert. I'm an empirical expert.
I think we were able to review, there were some wind tunnel tests that were done on the bridge, and we reviewed the results from that. And it was obvious that without these additional fairings that had been designed, the bridge would have had big problems overall. Now the fairings were designed, but they didn't totally eliminate the vibrations. So what the end result would have been once the fairings had been put on is unknown, but I'm guessing it would have been problematic. So they were not fairings that just totally eliminated all the vibrations.
It could probably have been solved, though. I think there are indications that some designers have worked with vertical baffles going in the longitudinal direction underneath the deck, which would break up this tendency for huge vortices, von Karman vortices, to generate and cause alternating vertical forces, and then thereby instability of the deck. But it is by far not an aerodynamic deck. And in order to make it aerodynamic, you would have had to enclose it completely with a steel plate on the bottom, which could have been done with additional weight. And then, of course, a different type of structure, in particular with regard to the pylon.
Thank you for that answer. Then there are a number of questions related to the analysis that was carried out during the investigations, and also the specialist software that you have been using. So here's one. I would like to ask what kind of dynamic analysis there was for the structure, any specific software?
Yeah. The software is called Solvia. It's a Swedish software package, and it's a sister software package to Adina, which was developed by Professor Bathe in the United States. So it has a very, it's a very well known. I mean, Adina in particular is very well known, and the core of that software has been around for a very long time. It does full linear, non-linear, geometric, material, static and dynamic analysis. So it's fully comprehensive finite element software, where you can also introduce your own type of material model. So you can actually create your own material models based on very specific conditions that you have. For example, with regard to reinforcement, in this case.
Excellent, thank you.
Yeah.
Here's another question related to the analysis. Was the analysis that was undertaken using actual conditions of the bridge at the time of the collapse?
Yes.
Dead load and actual materials, or was it a comparison with ideal code conditions?
No, it was not a comparison with ideal code conditions. It was an analysis of the bridge as is, meaning we even in the end took the values from the material test that we did, and we replaced the actual material strengths and yielding points within the software with the values that we got from the tests. So everything was as is in reality.
Thank you, Christos. Here's a question. I think we'll try to group again a couple of questions because you show quite clearly what happened to the remaining part of the structure. One of the participants is asking, during your investigation, have you compared the PET rebars and concrete strength of both towers? And if you did, what main differences did you find?
I would say no, we didn't. The main reason why we didn't do anything with the existing tower is because when we went to the existing tower, the cracks between the leg and the diaphragm had already formed. So we knew that we were on the verge of collapse. So dealing with that structure would have been very, very risky. In fact, we didn't even want to walk onto the structure. We just approached the structure from the outside because we felt it was that dangerous.
Thank you. I think that was the most sensible approach to it. Let me just scroll down a bit.
Yes.
Okay.
I think the next one, Tina, if you will allow me, it's Mr. Meikwan Yang is asking me, but I think it should be Christos about the dynamic amplification factor, which was actually part of the analysis that Christos was heading. So I think Christos, you should answer that one if you want to take it.
Yeah, if that's okay, Tina, the answer Mr. Yang here that the dynamic load comes from the rupturing process of the reinforcement. So when the reinforcement ruptured, then we ended up having this sort of sudden release of force occurring in the legs, which then led to an increase, or let's say a vertical acceleration of the pylon, which led to an overall increase of the vertical loads. So this is where we get this dynamic amplification factor of 2.0.
Thank you very much. There have been a number of participants who have asked whether the report is sort of available in the public domain.
It is. It has an ISBN number, but it has to be requested from us explicitly. So it's not available in a bookshop. It must be. We can, if someone wishes to have the report, they can send us an email, send me an email, and we will respond to that.
Thank you. I have seen that request from a number of the participants, and if more convenient, it could be organized through IABSE, and I'm sure Brenda will be happy to sort of organize in a simple way.
I thought that might be a good idea, that we could have that discussion about how this might be integrated into the IABSE library at some point.
Yes. Let me just scroll down. While I do so, perhaps I could ask a question of my own sort of the quality of the construction. Did you have any particular findings into the quality of construction in general?
I mean, maybe I'll just answer about the material, and then Klaus could talk about the details, but the material was not deficient. I mean, the material was generally very good. The concrete was of high grade, the steel, the same. The cables were generally, I mean, they were provided by a European, known European cable provider. So it was all of very good quality overall. I think some of the construction details were a little lax, but especially, for example, when it came to the dowels that were used to make the composite action between steel and concrete. But I don't know, Klaus, if you want to add something about that.
Well, I can try, but I was not on the site as you were, Christos. So yeah. My observations, I would rather maybe tie it together with, apart from the fact that there were minor changes on site. But primarily it is my feeling and sensation that this failure was not primarily caused by any means because of poor construction. as you said, everything seemed to be quite normal. Normal materials, normal behavior of the materials. Whether they were tested or not, I'm not sure, but they certainly did not indicate a deficiency of the sort that we have seen in other cases. So this is not the reason. There is a question again about the safety limit and so on. I can see that I can tie together with my answer. I think what Christos was saying is that we modeled the structure exactly as it was. At the stage of construction, it was, with the materials which were found on the place. And that model, as a static structure, was on the verge of collapsing simply when it came to the construction stage reached. The difference between pylon B and its cantilever and pylon C that was demolished afterwards was that there was one more deck section cast in place on the girder than on the B, which collapsed, than on the other one. So the logical thinking based on the analysis that demonstrated 99% use of the structure as it existed before collapse would have indicated that if they had undertaken the next casting on the pylon C, it would have collapsed. I mean, the analysis was apparently that good that it could replicate the situation that close. And I think all the drone inspections which were performed, which you haven't seen on the presentation here, but around the tower top, around the diaphragm and so on, indicated already cracks forming at the critical places, which eventually, if that was under the still standing part of the structure, indicating that if the next construction stage had been executed, the bridge would have failed. The other bridge half would also have failed. So it is not a construction deficiency as such, but it's the whole design which in many areas, unfortunately, was deficient and actually simply not able to sustain its own weight. Then the question, of course, was also raised, did an earthquake happen, or did we have any strong valley winds which could have initiated the collapse? But I think there was no really indication of that having happened.
There was no indication of that, but also we did some analysis to see what would happen if we had a shifting of the caisson and also some additional wind, and that was not sufficient to bring the bridge down if it had been properly designed, of course. But when you're at a safety factor of 1%, 1.01, then almost anything, a butterfly sort of touching the side of the bridge will bring the bridge down, right? So I think the main problem was the deficiency in the design, not some sort of external natural event.
Thank you for that very constructive answer. There are a number of questions to the foundation design, geotechnical investigations, and whether there could be sort of any deficiencies in the foundations that could also play a role in this collapse. Is this something the investigations have?
Yeah, we looked into that and we found that that was not the cause of the collapse. It could not have been the cause of the collapse. So there were deficiencies in the caissons and the overall quality of the construction, in the corrosion protection of the tendons, and in various aspects of the caissons, right? But all in all, they were okay. They were not what led to the collapse of the to the collapse of the bridge.
Thank you very much for a very clear answer. Here's a question to construction management, and it is addressed to you, Claus.
Mm-hmm.
Do you think the new construction management, such as bridge information modeling system, could help avoid this kind of tragedy, or at least avoid undocumented changes via WhatsApp?
I think any say professional approach to proper agreements between the parties. What is the responsibility of each party, and clear interface management between these various parties would, and of course, a clear understanding of the project that you are talking about. In other words, proper manning of the project, proper leadership of the project for each responsible party would, knock on wood, in all cases except the unfortunate one, be adequate to prevent this kind of mishap. When we're talking about, say, rather conventional structures where the behavior is generally known and researched and a proper experience exists. So it should such an accident like this one, to me, it is very, very unfortunate that it happened, because it simply should not happen. There are so many deficiencies, both design-wise, we are talking about technical here, not legal, but design-wise, transmittal of the design intent to the contractors, the construction, maybe we don't, but that's not the primary cause in itself. And then, of course, above all, the organizational deficiencies and lack of, say, justice in terms of documenting what you're doing, checking what you should check, and so on. If this had been done in a proper way, which is done normally, luckily, I think all the projects I've been involved in the past 55 years, I've never seen anything like this. I mean, this is very unusual. So it shouldn't happen.
Thank you, Claus.
It's perfectly avoidable. It's perfectly avoidable.
There's another question related to sort of the conditions on site. Were you able to interview any workers to know whether anyone noticed cracking
That's for you.
prior to the collapse?
Yeah, no, I think that they, as far as we understand, they didn't notice the cracking prior to the collapse. But after the collapse, they did notice it in the other pylon. So we were shown the cracking in the other pylon when we arrived. So I think that's how it was.
Thank you. Then there are some questions to sort of what is going to happen next. Is a new bridge going to be built? In that case, will it be a cable-stayed bridge with a similar span? Can the foundations be reused? Do you have any insights to sort of future plans?
Yeah, I think what we found was that the foundations could probably be reused. And our understanding is that there's a French consortium that is involved in the redesign of the bridge. I'm not sure at which stage the construction is at, if at all. But my understanding was that there was a French engineering firm that was involved in the redesign.
Thank you.
And it is a cable-stayed bridge also.
Thank you. Some questions now going back to sort of what happened on site. Were there any monitoring systems in place during construction that could have given a warning of what was happening?
No, there were a few monitoring systems, but nothing comprehensive and nothing that would have given, as far as I can see, given any indication that there was an imminent collapse, because it was so sudden. As I said, it was the behavior of the diaphragm was not ductile. So if we had some instrumentation there might have been some sort of slight cracking that could have been picked up or observed. But other than that, there was nothing to indicate that the collapse was imminent.
just going back to sort of the overall conclusions of this investigation, there have been a couple of questions asked in relation to how does it compare to other investigations. There's a reference to a report by another group of experts. Have your findings been compared and discussed with other teams of experts? And now I'm just talking sort of in a technical manner, not legal aspects.
No, I don't think we've done that comprehensively. I mean, we did pick up on other reports that had been issued, like that of Modjeski and Masters. We had similar conclusions on the overall mechanism, which is the lack of restraint at the knees. But we had a lot of differences in terms of the detail. I think we generally, maybe because of the purposes of the investigation as it was commissioned by the insurance company, we ended up being a lot more detailed in some of the understanding of the deficiencies of the structure overall. But we didn't make any kind of critical, when I say critical, I mean it also in a positive way, any kind of critical comparison between our report and what has been done before, like, for example, the Marison Committee report of 73 or other similar reports. I personally offered to provide the report and have a discussion to those who were undertaking the Morandi Bridge collapse investigation, but that they never came back to us to discuss with us so that we could make that sort of input and comparison.
Thank you. I think here's a question, and you probably already touched a bit on it, Christos. Present trend international seems to be to compress the design time to an unrealistic sort of number.
Yeah, I think it was Klaus who said that.
Yeah, and this is seriously impacting the safety. People seem to have forgotten the Marison Committee report of 73. Do you have any additional views to offer on this aspect?
I think I would like to add a little comment to that one. I think it's a very pertinent question because I think it is a habit of the time that everything has to go faster and faster. And there is a tendency to say, well, we can just, with the computers of today, we can put everything into a computer and get the results tomorrow. Bridge design is not a standardized procedure. Every project is a prototype in a way. Different conditions, different loadings, different environmental conditions, different construction practices, different consulting practice, design practices, and so on. They are all different, even though we try to, structural engineers, to sort of reuse what we have done in the past. So it is different, and we have to think over. And also we have a tendency to start construction before the design is completely finished, which means a construction follow-up of the intent by the original designers is extremely important. And there is a tendency amongst clients also, in order to distribute work amongst several parties, to split the piecemeal, the cake into many pieces so everybody can have a piece of the cake, which increases the risk of mistakes and deficiencies fall between two chairs or many chairs. So I think there is a little bit of a warning here, and things cannot go faster than they can. The human mind needs to be going along. It's not only because I'm a slightly elderly person it's that I say this, because it could come from an old person on his way out. But on the other hand, I think it is true. We have to be careful not to race things through and think everything can be done automatically. The good old guy, Eiffel, whom I admire very much, who back in 1880s designed the Eiffel Tower, and before that one, a beautiful arch bridge over Douro River in Porto, which I looked upon just a few years back. It's an admirable piece of meccano, of steelwork, and every piece of this bridge has been designed without a computer, and is probably more optimized than what you see people do today. So what I think my mission is, also at this university here, where I have been fortunate to be asked to participate a little bit in the education, is to say, think before you start putting things into your computer. Think about the structure and the way it is performing, and where are the risks? Where are the weak points? Can they be made better? Because nothing is stronger than the weakest point. And then, as Christos has also stressed several times, make the structure ductile. So at least you get warnings and plastic redistribution of forces. If the forces cannot go elsewhere, it will fail. But if they can go elsewhere, it might partially fail, but you have a chance to save it and save lives. So I think, in summary, long answer to a short question, but it is an important question. The owners should be aware that this is serious business. We are talking about big forces that you can just play around, not play around with. We're talking about materials. We're talking about something that stands for maybe 200 years. It is very, very important to be aware of this and give the necessary time for proper reflection and proper designing and proper construction, and follow up by some key personnel all the way through. Thank you.
Thank you, Claus. I think that was really useful food for thought. I think we are close to sort of wrapping up, because I realize we have gone more than 45 minutes over the allocated time, and that just demonstrates how important the topic is and the interest. I think there is one comment here that I would like to read out aloud, and then I think we will sort of start closing down. From Einar Tejngaard: the design is faster and faster, but the checking is more and more complex. The complexity with several checking levels have a tendency to dilute the responsibility more than tightening the checking. Do you have any sort of final reflections on that comment, Christos and Claus?
You have one, I have one.
One each.
No, I must admit that I like the idea that that there is an engineer or a group of engineers who are responsible to a large extent for the design of the structure overall. But at the same time, the checking is super important because we're just humans. And in the process of designing something, we get caught up in our initial thoughts and our initial design, and sometimes we lose sight of what might be the overall deficiency. So I think it's really good to have someone, even if it's a group or a company or some engineers which we think are not as competent as we are. It would be very good to have them have a view over our shoulders of what we're doing overall. So that would be my comment. But Claus, I think you can finish with a more comprehensive.
Well, we can keep on talking about this very important subject, but let me just tell you what happened when I was employed as a young engineer 55 years ago. I was told about something called intelligent check. So every project that was designed by whoever it was always reviewed by a senior person, not necessarily senior in the terms and age-wise and so on, but one more experienced who had seen similar things before. And instead of detailed checking, that can be done. But the intelligent check, which is normally done within, I would almost say, hours of an experienced person, would catch, I think, 99% of all mistakes, simply by, as I said earlier, backside of an envelope, rough analysis, and sort of indicate, is there a problem, an imminent problem here or not? And then you can always detail analysis it afterwards, but to see if that sensation was correct or not. But the sensation of a so-called intelligent check by an experienced engineer, fast, not very expensive, but extremely useful. And I can only emphasize that idea. I personally have caught quite a bit of things by just looking at drawings and asking the designer, did you think about this problem? How was that solved? And then very often the designer says, maybe I should just look at that. So that can catch a lot of things. Something to think about.
Thank you very much, both of you. And I can see in the comments and answers there are lots of thank you to both of you. So I think with that sort of good reflections from both of you, I think we'll start wrapping up. And definitely from my side, I would thank you once again, Christos and Klaus, for a brilliant presentation and for sharing knowledge so openly. This is in the best interest of our profession, because that's the only way really to learn from mistakes and avoid making them again. There are tools to give them a big virtual round of applause. So if you know how to use them, this is the time to do so. And thank you for sharing your insights and these vital lessons learned. While you find the applause button, I would also like to thank IABSE for hosting this webinar, to Firat and Brenda in Zurich for facilitating and taking us safely through everything. As far as I can see from my end, it has worked perfectly. And then I would like to advertise there are a number of webinars coming up on this IABSE platform. So please stay tuned. The next webinar organized by the Danish group of IABSE is on the 10th of June, and it's on the topic of concrete plasticity and the whole history of concrete plasticity. So thank you once again, all of you, for participating. I think we were over 300 when it peaked. And to everybody in this pandemic, please keep safe and healthy. Thank you.
Thank you very much.
Thanks for an excellent conduction of this webinar. That was a good experience. Thank you.
And thank you for your additional time. I think we overrun by a factor of 2.
Bye-bye.
Thanks to all.